In this lesson, we're going to talk about one of the things that frustrates students the most in chemistry, and that's going to be rounding to the proper number of significant figures. Now, in math class, you learned a long time ago how to round, but it's really not the job in math to teach you why you round. This year, maybe for the first time ever, I'm trying to teach you that rounding is important because we make measurements and we assign number values to specific place values in numbers, and those place values indicate the accuracy, the precision of our measurement. And like in any measurement, there is inherent human Murphy's Law error, and we know from our lab that error can't be avoided. And that last digit in any measurement should always be a guess that best approximates the capabilities, the maximum capabilities of the measuring device. In other words, it's a guess. The last digit's always a guess, so there's error. So when we combine measurements, we add them, we subtract them, we multiply them, we divide them, like we're finding area or volume or density, any of these things, any of these operations, even perimeter, where we're combining measurements, our final answer has to reflect the amount of error that is in our initial measurements. So we've grouped our mathematical functions roughly into two pieces, two rules. In rule number one, we discuss what we have to do when we combine numbers for rounding and adding and subtracting. So read rule number one with me. When you add and subtract, your answer is rounded based on place value. And that's the important thing to remember, place value. You line your decimals up to do addition or subtraction. Your answer is rounded to the least precise place value in the measurements you're adding or subtracting. So what least precise generally means in layman's terms is that place value where the sig figs, or the guess, let me change that up. It's the place value where the guess first shows up in your answers. Let's look at number one. I'm going to line these numbers up, 35, 35.6, and 38. Now, if we look at each of these three individual measurements, in the 35, the 5 is the digit that is the guess. That's the ones place. So a guess happens in the ones place. In the second value, the 6 is the sig fig that is the guess. So error happens in the tenths place. Well, the ones place is further to the left than the tenths place. And the third digit, the 8, is also in the ones place. So again, the ones place is the least precise place value. It is the farthest to the left where the guesses show up. So I've already given you the answer to that one. Unrounded, it's 108.6. We need to round this number to reflect the place value where error first shows up, and that's going to be the ones place. So using my rules from rounding from middle school math, the 6 behind the 8 is going to cause me to round this up to 109. We don't just drop, we round. If it's 5 to 9, we round up. If it's 0 to 4, we round down. So this 6 tells me to round up. And you're thinking, well, how the heck? How do we just make changes like that? Well, it goes back to these values over here. We don't have much confidence in the 5 or the 8. They're both guesses. So then how can I, in my answer unrounded, report it as 108.6 when I'm not even sure the ones place is even accurate? So our answer can only be as accurate as our least precise place value. Let's look at the second one. Again, I've given you the answer already. We're just going to round it. So looking at my measurements, number 2, the last digit is in the hundredths place, and then this one's the thousandths, and this one is the tenths. The tenths place is the one farthest to the left, so in my answer I'm going to round to the tenths place. So looking at the number behind it, 7 is going to cause me to round that up. So I'm going to have 223.1. Again, we do not drop, we round. In number 13, number 3, let's look at the place values. In 12, the ones place is the guess. In number 11, the ones place is the guess. In the third measurement, the tens place is a guess. That's farther to the left than the ones. And in the final measurement, the hundreds place is the guess. So in my answer here, I can't have any confidence past the hundreds place, which is where the guess first appeared. So I'm going to round it to the hundreds place. The 4 tells me to round down. So this answer will be rounded to 100. And number 4 is a subtraction problem. We're not going to do anything different. We still do place value. So in number 4, I see the tens place, the tenths place, tenths again, and the hundreds. So out of those 5 measurements, in this one we see the guess occurring farther to the left in the tens place. So I must round this answer to the tens place. The 5 behind it tells me to round up, so that will be rounded to 120. Now historically, students really have the hardest time with this rule that we've just gone over, the adding and subtracting. I don't really know why, because to me, I know I'm a teacher, but to me this one makes a lot of sense. It's about where the error occurs and what place value does it first happen. Just line it up and go to that place value. It makes a lot of sense. Moving forward, I think the multiplying and dividing is harder to explain, but students have an easier time with it. Let's see if you have the same kind of path here. Rule 2 together. When multiplying or dividing, your answer can only have the same number of significant figures as the measurement with the fewest number of significant figures. So this time, we're not interested in where the error is or where the sig figs end up. All I care about is how many sig figs are there. And some of you may be thinking, how is that even possible? I don't understand how the number of sig figs matters. Well, it's not an easy explanation. The best I can tell you without confusing you too much is to say that when you multiply and divide, or exponents, or any of these things, the error accumulates at a much faster rate than if you just add and subtract. So we lose the integrity of those place values and actually cause the error to expand, if you will, into larger place values. So we don't get to have as many measurements usually, or have as many place values of integrity when we multiply and divide. Alright, so just to get down to the bare bones of it, the rule says for multiplying and dividing, our answer can only have as many sig figs as the measurement with the fewest. So looking at number 5, that's a multiplication problem. Let's look at each measurement and see how many sig figs are in each. In 56.49, there are 4 sig figs. And in 2.4, there are 2. And in the final measurement, there are 4. Remember that 0 counts. So of those 3 measurements, 2 is the fewest. Our answer can only have 2. So when we round that, we start from the left. That'll be the first one. And this 4, this place value here, will be the second one. So it will either stay as 4 or round up to 5. That depends on the number behind it. The 2 tells me to keep it as it is. We do not drop, we round, which means we have to add the placeholders to maintain the 1 in the thousands place and the 4 in the hundreds place. So that number, that measurement is rounded to 1400. In number 6, it's division, but the same rule applies. In the number 70, we have 2 sig figs. And in on the quotient here, we have 3 in the denominator. So our answer, again, can only have 2. And as I look at my very long answer here, the 8 stays, the ones place becomes the battleground. The 7 is going to tell me now to round that up. And I'm already at the decimal, no need to add placeholders. Do not add 0.0 because that would be adding a sig fig. So you stop there for that one, 83. In number 7, multiplication, we have 3 sig figs and 3 sig figs. Oh, now what? But our answer only has 2. We have a case where we didn't report enough accuracy. This answer is erroneous for the opposite reason. I didn't give enough significance. So I actually would come out and make 41.0 and show that this product has one more place value that we can count on. In number 8, I have a larger problem here. I've got 4 values, 4 sig figs here, 2 here, and 5 here. So again, my answer can only have the 2. Looking over here, 9 comes first. The 4 will be the second one, or that place value will be the second one. And the number behind it tells me to round down. So that will be 94. No need for zeros again. And finally, we have a combination here. I have order of operations inside the parentheses that are adding and subtracting. So we're going to do those together. I calculated the first sum here, unrounded, to be 22.4. And the denominator is 10.2 minus 8. So 2.2. Again, both of those are unrounded. What we're going to have to do now, before we divide, is actually round using the adding subtracting rule first. So let's look at the numerator. The numerator was made in an addition problem where the guess was in the hundredths place and then 1 was in the tenths place. So we have to round our numerator to the tenths place, which turns out to be fine. It's already there. So we're in good shape. Then for the denominator, in our 2 measurements, we had a tenth place and then a ones place. So my denominator is not good enough. I have to round my denominator to the ones place, which is just 2. Now I'm going to divide 22.4 divided by 2, and that comes out to be 11.2. And now I need to round that according to the rules for multiplying and dividing. In the numerator, there are 3 sig figs, and in the bottom, there's only 1. So I have to round this answer to only have 1 sig fig, which means I round down to 10. So that may make some of you uncomfortable having to round down that far. A lot of you don't inherently see why 11.2 needs to be rounded down to 10. And my answer probably won't make some of you happy. It's because the error that's in those measurements only allows me to have confidence in that one significant digit, which is in this case the tens place. We need more practice at this, so come see me if you need to talk about it, and let's get some practice done in class.